Hello students, today we're going to talk about functions and relations, and embedded in this lesson we're also going to talk about domain and range. So we're beginning with talking about what a relation is. Really, a relation is any combination of or matching of elements. And so when we start talking about a function is a relation that has to abide by specific rules. So in this definition, the definition of a function, given a relation x and y, we say that y is a function of x. If for each value of x, right here, if for each value of x in the domain, there is exactly one value in the range. So what that means is each x value can only map one time. So part A, this example part A, this is not a function because the x value of 2 is trying to map to the number 3 and 4. It's trying to match to two values. And when it does this, it is not a function. It's a relation. Relations pretty much have no regulations at all. But this is not a function because the x value can only match to one y value. Part B, you have an x value of 1, an x value of 2, and an x value of 3. So x was never repeated, so it is a function. And in the third example, part C, they're matching. And when they're matching, you really only have to look at the x values and make sure that there is not more than one line exiting from each x value, because the x can only map one time. So this is also a function. Now, normally we actually determine if something is a function or not by looking at its graph, because that's pretty quick and easy. And to determine from a graph if you have a function or not, we use the vertical line test. So a vertical line test says, given a graph of the function, as in this first graph, which is a circle, if you strike a vertical line anywhere on that graph, if it dares to cross the graph more than once, then it's not a function. So in the case of a circle, when I strike a vertical line, it crosses it twice, not just once. So this circle is not a function. Now the next example, if I strike vertical line, anywhere I want to put a vertical line, it will never cross the blue graph more than once. So this one is, yes, a function. The third example, I start striking vertical lines and it looks good, but there is one vertical line that's not going to pass this test. If I come straight down the y-axis, I cross the graph at these 2 points. So it is touching it more than once. So this one is not a function. Now if one of these points, had it been a hollow circle and the other filled, it would have been a function. But since they were both filled circles, then your x value of 0 is mapping twice. 0 is mapping to 1 at this point, that's a -1. And 0 is mapping to a -4 at the second point. So the x value is being used twice, making it not a function. Now we have this thing called function notation. We use this a lot in college algebra. It says evaluate f of x, evaluate this function, equaling 2x squared minus 3x plus 1 for the given values. Now inside the parentheses is your x value. So inside these parentheses, this is an x value. So all you do is take this x value and replace every x in the original equation with that number, in this case -3. So this would be 2 times a -3 squared minus 3 times a -3 plus 1. This becomes 2 times -3 squared. -3 times -3 is a positive 9. Minus 3 times -3, which is another positive 9, plus 1. So this is 18 plus 9, which is 27, plus 1, which is 28. So the answer is 28. You were given an x value of -3. So it's actually pretty logical that the result must be a y value. You were already given the x, so the y value must be 28. As a result of all of this, you can say the ordered pair with the x value of -3 and the y value of 28 would be a point on that line. If they say f of square root of 2, they're just trying to give you a little practice with these radicals. You would just put the square root of 2 in place of every x value again. This would equal 2 times, the square root of 2 squared is 2. So this would be 2 times 2 minus 3 square root of 2 plus 1. 2 times 2 is 4. And then you could take the 4 and add it to the 1, but the radical term has to be left alone, and this would be your result. This would be your function value. So again, if I wanted to write an ordered pair, they gave me the original x value in the parentheses of the square root of 2, and the y value would be 5 minus 3 square root of 2. The next one looks a little weird. They're saying instead of use x, use a. So okay, everywhere there's x, I'm just going to throw this capital A. So this would be 2 capital A squared minus 3 capital A plus 1. And that's it. There's not a darn thing you can do to that. Okay, that's the end. That is the answer to the question. The next one is replace your x value with 3 plus z. So this becomes 2 times 3 plus z squared minus 3 times 3 plus z plus 1. Okay, now when I have a binomial square, this is the 3 plus z times 3 plus z minus, I distribute this -3. -3 times 3 is -9, and -3 times z is a -3z. And then I add a 1 to the end. Now anytime you have a binomial times a binomial here, I guess I'll come off to the side. If you have 3 plus z times 3 plus z, this multiplication problem we often refer to as the FOIL method. So we take the first terms, 3 times 3 is 9. The outside terms, which is 3 times z, which is 3z. The inside terms is again z times 3, which is 3z. And the last terms, which is z times z, which is z squared. So ultimately, this is 9 plus 6z plus z squared. So returning back to really the question, this is now 2 times 9 plus 6z plus z squared minus 9 minus 3z plus 1. And yes, you could take the minus 9 plus 1 and get your -8. Okay, continuing. Distribute this to 2 times 9 is 18. 2 times 6z is 12z, and 2 times z squared is 2z squared. Okay, finally, I'm going to put this in what we call descending order. I'm going to write the 2z squared first. Then I have a 12z minus 3z, which is 9z. Then I have an 18 minus 9, which is 9, plus 1, which is 10. And that is your answer to the question. Another interesting fact now is, remember, this which I circled in the parentheses would be the x value of an ordered pair, and the y value of the ordered pair would be 2z squared plus 9z plus 10. But this is the answer to the question that I'm now putting a square around. That is what f of 3 plus z equals. Alright, part B, kind of a transition now out of function notation and out of functions and relations. Determine the x and y-intercepts of a function. Okay, what in the world are x and y-intercepts? Well, the best way to see an x or y-intercept is to view it from a graph. So suppose I create a graph here, and I'll just go ahead and draw a straight line between them. The x-intercept is the point where the line crosses the x-axis. This is the point where the line crosses the x-axis, which is the ordered pair 4, 0. So the x-intercept is the point 4, 0, or you could say the x-intercept occurs at 4. The y-intercept here is the point 0, -2, where you cross the y-axis. So the y-intercept is the point 0, -2, or a value of -2 is your y-intercept. Now let's look at another example. Suppose I choose to go through these points, and I'm just going to sketch a graph something like this. Okay. And again, they ask the questions, what are your x-intercepts and your y-intercepts? Well, in this case, you have 1, 2, 3 points where you're crossing the x-axis. So you have 3 x-intercepts. You're going through the point -3, 0, the point -1, 0, and the point 4, 0. You have 3 x-intercepts. Y-intercepts is where you cross the y-axis, and you can only have one of these or it would not be a function. We are crossing the y-axis at the point that you see me creating, which is the point 0, +2. Now notice in these ordered pairs that all of your x-intercepts have a y value of 0. That will always be true. And notice that your y-intercept has an x value of 0, and that too will always be true. So if you look above, it says, up here in number 1 now, up here, the x-intercepts are the real solutions to the equation f of x equaling 0. Well, here is your x, so this is your y value. So all of your x-intercepts will have y values of 0, which we just discovered. The y-intercept is given, I'm back up here, the y-intercept is given by f of 0. Well, in this case, remember, the value in the parentheses is your x value. So your y-intercepts occur when your x value is 0, which is what we also determined when we drew the graph and selected the y-intercepts. Now it says find the x and y-intercepts, not given a graph, but given an equation. So now we know that anytime I have an x-intercept, and I might have more than one, my x-intercepts occur when the y value is 0. My y-intercepts occur when the x value is 0. Okay, in function notation, f of x is your y variable. So you can replace your f of x with the y variable. So if I want to find my x-intercepts, I need to take the y and replace it with 0. Okay, so my x-intercepts would be, if I start with my equation, I need to replace the y value with 0. Now I need to solve it. So if I add 4 to each side, then it would say 4 equaling x squared. Now to get x, not x squared, I need to apply the square root. When I apply the square root, I need to remember to put the plus minus in front of it. So plus minus the square root of 4 is plus minus 2. So there are two values. One is a positive 2 and one is a negative 2. So I have two x-intercepts. They are occurring at positive 2, 0 and negative 2, 0. Now, the y-intercept, I think you're going to discover, is a little easier to come by. It occurs when the x value is 0. So if I put my equation down and I replace the x value with 0, I will very quickly and easily come up with the y value of the ordered pair. So my y-intercept is occurring at the point 0, -4, for f of x equaling x squared minus 4. Part B, the same thing. I'm going to rewrite this. I'm going to take it out of function notation, and then I'm going to find my x-intercepts, 1 or 2. I could have many x-intercepts, but only one y-intercept. My x-intercept occurs when I replace the y with 0. So this becomes 0 equaling 9 minus x cubed. Now if I come in here and I subtract 9 from each side, it will then say -9 equals a negative x cubed. Now I need to let go of the negative, so some people multiply both sides by -1, some people divide by -1, but either way, your results can be a positive 9 equaling x cubed. Now to get the x value, I take the cube root. So the cube root of 9 equals x. So I only have one answer in this case for an x-intercept. My x-intercept is going to occur at the point cube root of 9, 0. My y-intercept occurs when my x value is 0. So going back to my equation, if I replace the x value with 0, I get y equaling 9. So my y-intercept is going to occur at the point 0, 9. One more example of this x and y-intercepts from my equation. The first thing I'm going to do is take it out of function notation. Then I'm going to find my x-intercepts and then my y-intercept. Okay, my x-intercepts occur when the y value is 0. So 0 equaling 2 minus the square root of x. I'm going to subtract 2 off of each side of this equation. And when I do, my result will be negative 2 equals the negative square root of x. Again, I need to get rid of the negative, so I either divide both sides by negative 1 or multiply. And when I do this, I get a positive 2 equaling the square root of x. Now to get x, this time I square both sides. So then I get 4 equaling x. So now my x-intercept, there's only one again, is occurring at the point 4, 0. My y-intercept, go back up over here now, going back to this new equation, is going to occur when the when the x value is 0. Well, the square root of 0 is just 0, so the y value is 2. Therefore, the y-intercept is occurring at the point 0, 2. Alright, part C. Now we're making a transition into finding domain and range. So we've already talked about how a function must pass the vertical line test. We've talked about function notation. We've talked about x and y-intercepts, and now we're going to talk about domain and range. Domain refers to x values, and range refers to y values. We usually write these in interval notation. So your domain will be an interval of x values, and your range will be an interval of y values. So now it gives me examples. It says determine the domain. In this case, it's just asking for domain, and then write your answer in set and interval notation. Okay, when someone asks you for the domain, they're asking what x values can I put into this equation? Well, you can pick any old x value you want. So your first thought is x is any real number. And then you look again and you say, do I have a fraction or do I have a square root? Because that causes problems. Well, you do have a fraction. And when you have a fraction, the bottom of a fraction cannot equal 0, or the fraction is undefined. So in this case, if I fool around and let x be negative 2, the denominator would be negative 2 plus 2, which is 0, and I cannot have that. So x is any real number, but x cannot be a negative 2. That is your domain. Well, you've got to write it a little better than this. There's two forms of writing it. One form is to write it as a set, and you may not be familiar with this. This may be the first time you've seen it, but it's not difficult. You would draw these braces, and you would put x and a vertical line, and then you'd put x not equal to negative 2. What that says is all x values such that x is not equal to negative 2. If I wanted to write my answer in interval notation, it would be a little easier to explain this if I first present it as a graph. So I'm going to show you from a graph all values excluding negative 2. All values not negative 2. This would be a graph of all values excluding negative 2. So in interval notation, this is two regions. On the left side of negative 2, you're looking at numbers negative infinity to negative 2. On the right side, you're looking at negative 2 to infinity. So when you put these together, this is your answer for your domain in interval notation in which you're excluding one number, that number being an x value of negative 2. A second example, again, a fraction. So your original thought is my domain is X is any real number. Then you look again and say, do I have a fraction or do I have a square root? Crud, I have a fraction. Therefore, I need to be concerned about this denominator because that denominator cannot equal 0. Well, some of you can look at that and say, okay, X can simply not be 4. And that is correct. X cannot be 4. Others of you may not be able to pull that number out of your head so quickly. And if you can't, just go off to the side and say, okay, what in the world would make 3x minus 12 equal 0? Well, if I add 12 to each side and I divide by 3, there is the number that would make the bottom of the fraction equal to 0. To write this domain, and remember I'm finding the domain, to write this domain in set notation, it would be all x such that x is not equal to 4. That is your domain in set notation. I should have squared it off on the other side also. To write this answer in interval notation, again, I'm going to demonstrate it by a graph first. If I eliminate 4, it's all numbers with an open circle at 4. As an interval, this would be written, the left side is negative infinity to 4 with an open parentheses, and the right side is 4 to positive infinity. These two things, these two representations, say the same exact thing, and this is your domain. This is true on the first example. These two are the same thing. They're giving you the domain. One is in set notation and one is in interval notation. Here's another example. It's still a fraction. What is the domain? What x values can I put into this fraction? Your first thought is x is any real number. And then you stop and you say, hey, it's a fraction, I've got to be careful with this denominator. What will make this denominator equal 0? Well, there are two values. One is x better not be 4, and the other is x better not be negative 4. Okay? Again, if this does not come to you naturally, then you would go off and say, what makes x squared minus 16 equal to 0? You would factor this, and then you would set each factor equal to 0, and you would come up with these two values. So that's how you would get the 4 and the negative 4. I have some beeping going on in the background, so let me pause this for a second. Okay, so now that we know that, when we write this is your domain. When we write the domain in set notation, this is all x values, such that x is not equal to 4 and not equal to negative 4. That is your domain in set notation. We also need to write this in interval notation. Now before I write it as an interval, again I'm going to just quickly graph this for you because it makes it a little easier. I'm going to be coming along not negative 4, not positive 4. That represents all of these x values in this domain. How do I write this as an interval? 3 intervals. This left part is negative infinity to negative 4. The middle part is negative 4 to 4. And the last part on the right side is 4 to infinity. This is your domain written in interval notation. Both of these in square boxes are saying the same thing. They are both the domain for this function. One is in set notation, and the other is in interval notation. Alright, part C. Look how similar part C is to example B in blue. It's exactly the same with the exception of there's a plus sign in this denominator. So now x is any real number. I'm going to choose anything I want. And then I look again and say it's a fraction. Is there any way to make the denominator equal 0? Well, if I put a 4 in for x, this would be 4 squared, which is 16 plus 16, which is 32 in the denominator. That's not 0. If I put a negative 4 in for x, negative 4 squared is a positive 16, and 16 plus 16 repeats the 32. There are no values that will make this bottom of this fraction equal 0. So therefore, the answer is all real numbers. There are no values that would make that fraction undefined. No values that would make the denominator equal 0. So, in set notation, this looks really strange, and you might not see this very much. All x values so that x is an element of the real number system. That is written as set notation. You probably won't ever have to answer a question like that, so don't be terribly concerned. The interval notation is what's important, and it would be negative infinity to infinity. So this is your domain in set notation, and this is your domain in interval notation. Okay, here's one that has a square root in it. When you have a square root, you always are concerned with the number under the square root being positive. It cannot be a negative number. So in this case, it's a little different. Here, x can be any real number. You pick any number you want to put into this equation. But then you pay attention to the fact that you have a radical. What that means is that the radicand, the information under the square root, must be positive or equal to 0. X plus 4 must be a positive number, and it can also be 0 because the square root of 0 is 0. So this becomes x greater than or equal to a negative 4. Okay, so in set notation, all x values such that x is greater than or equal to negative 4. Now, how would that be written as an interval? Again, I'm going to show you a graph very quickly. Greater than or equal to negative 4 is to the right of negative 4 and the value of negative 4. So in interval notation, it is negative 4 to infinity. Here is your domain in set notation, and here is your domain as an interval. Alright, part F. Very similar to part C. I don't know why in the world I've got these lettered incorrectly. In this example, you're thinking the domain is any x value, and I'm going to pick x to be any number I want it to be. Then I stop and I look and I check to see if I have a square root or a fraction. This is a square root. So there will be restrictions. The restrictions will be placed on the fact that 3x plus 9 better be greater than or equal to 0. When you subtract 9 and you divide by 3, you come up with the result that x better be greater than or equal to negative 3. So your domain in set notation is all x values such that x is greater than or equal to negative 3. Written in interval notation, I will first show it as a graph. It would be from negative 3 to the right. So as an interval, it will be negative 3 to infinity. This is your domain in these square boxes. One is in set notation and one is written as an interval. Okay, now these two examples, they are fractions with square roots. Both, not h, f. F is a fraction and a square root. So the domain is saying what x values can I place into this function. So you start thinking x is any real number. Then you look and say, okay, I've got a radical, so that's going to restrict it. That means that x plus 9 better be positive or equal to 0. But in this case, x plus 9 cannot be 0 because it's in the bottom of a fraction. So now, x plus 9 could only be greater than 0, not greater than or equal. So x is greater than negative 9. So your domain in set notation is all x values such that x is greater than negative 9. That is your domain written in set notation. I can show it as a graph because that makes it easier to turn it into interval notation. Greater than negative 9 is to the right with the parentheses. So in interval notation, it is negative 9 to infinity. This is your domain. written as a set and then also written in interval notation. This example, part H, you're looking for the domain. So you're looking for any x value you can put into the function. We're going to start by saying x is any real number. Then I look to see, is this function a fraction, or is this function does it have a square root in it? It does not have a fraction. It does not have a square root. It has absolutely no issues of concern. Therefore, x really can be any real number. So you go back to set notation where it looks really strange, which this notation says all x values such that x is an element of the real numbers, meaning x is a real number, and in interval notation it would be negative infinity to infinity. This is your domain written in set notation and then written in interval notation also. Now they can also ask me to determine the domain and range given a graph. Alright, if I want to start with a graph, maybe I have this point over here, -4, -2, and maybe my graph looks something like this. Well, your domain is the x values used for this graph. This x value is starting at a -4, and then the graph continues to the right. This keeps going. So your x values are going from -4 to infinity. That's an interval, not an ordered pair point. That is an interval of values. Remember, your domain is your x values. Your range is y values. So now what are my y values? My y values are starting at a low point, a low value of -2, and then they're going up. It's going right, but it's also going up. So your range starts at a -2 and goes to infinity. Now I've made a mistake and I should have put a closed bracket on this -4 because that point is a filled point. If that point was hollow, you would use parentheses. Now suppose I have one like this. Alright, there's my graph. So on the left side, okay, let's just start with the domain. Your x values are your domain, which make a graph. On the left side, you're starting at an x value of -4. And on the right side, you're going as far as an x value of 3. So your domain is from -4 to 3. Your y values are what are your range of values that create this graph. Y values. Now on the left side, your y value, well, hang on a second, I'm sorry. Your range should be low to high. Start on the lowest point of the graph to the highest point. Your lowest point down here is at the point 3, -1, and your y value is a -1. Your high point is not over here. Your high point is up here. So you got as high as a y value of 3. This is the point -3, 3, and you went as high as the y value of 3. So your range is from a low of -1 to a high of +3. Let's just do a linear graph in general. And then suppose we have something like this. Where there are arrows on both ends. Okay, so your x values represent your domain. On the left side, because x values are left to right, on the left side, this graph is going down, but it's also going in the left direction forever. So it's going toward -infinity on the left. On the right side, you're going rightward forever, so you're going to infinity on the right also. Your y values represent your range. This is low to high. X's are left to right. Range is bottom to top. How low does this graph go? It goes downward forever. So it's going down toward negative infinity. How high does it go? It goes upward forever, so it goes as high as positive infinity. That is your range. Now we have some really pretty graphs given to us in blue. Okay, so we're going to say our x values represent our domain. And in this picture, my x values are left to right. This looks like it's only going up, but really it is also going leftward, infinitely leftward. So your domain to the left is negative infinity. On the right side, it looks like it's only going up, but it's also going in an angle to the right. So it is going to the right to positive infinity. Your y value is your range. How low does the graph go and how high does the graph go? This is its low point, and at this point the x value is 1 and the y value is 2. Remember, your range is the y values. So it starts at a low y value of 2 and it goes upward to positive infinity. Next example, your x values are what create your domain. Your domain is left to right. This graph is going leftward infinitely, so it's headed out toward negative infinity. It's going rightward, hard to tell. It looks like it's going straight up, but it is not. It's like never will it go straight up unless you have a perfectly vertical line. It is, I'm highly exaggerating, but it is also going toward the right as it goes up. So it's going to positive infinity in the rightward direction. Your y values are what give you your range. Your low point's way down here. And your high point, well, it's going left, it's going to the right, but it's going up. So your low point, what in the world is this? That's a negative 12. I guess that's a negative 10. So this looks like it's about a 3, negative 10. Now remember, your range is your y's. So you're starting at a y value of negative 10 and you're going upward forever. Okay, one more example. Your x values are what represent your domain, which is left to right. This is going leftward and down toward leftward toward negative infinity. It is going rightward. Here it looks like it's only going down, but it is going to the right also. Unless it's a perfect vertical line, it is at an angle. So it is going from negative infinity to infinity. Your y values represent your range, and it is going downward. The low point is negative infinity, and the high point, it looks like this is as high as it goes right here. This is the point 2, 1, 2, 4. The y value is your range. It's going as high as positive 4. Those take a little practice. Now it's taking me back into function notation, and this is going to be the last part of this lesson. This is a long recording. Use the graph to answer the following questions. Okay, in parentheses, this is your x value. So it's saying x is negative 3. So evidently they want an answer which is a y value. So where is x negative 3? 1, 2, negative 3. This is the point on the line at which x is negative 3. This is the ordered pair point, negative 3, 1, 2, 3, negative 3. So the y value is also, oddly enough, negative 3. F of 0, x is a 0. X is 0 at the origin, and the point where the line has an x value of 0 is above. This is the point 0, 2. So the y value is 2. Find all x values for which f of x equals 1. Here is your x, so this must be a y value. Y is negative 1. Where y is negative 1 is this point right here. This is the ordered pair point negative 1, negative 1. So oddly enough, the x value, which is what they're asking for, the x value is also negative 1. Find all x values for which f of x equals 1. Here's where your x value goes, so this output must be y. Where is y equal to 1? Right here, this is a height of 1, and this open circle is a height of 1. You cannot count the open circle, but the filled circle is the point 2, 1. So, f of x equals 1. Y is 1 when your x value is 2. Determine the x-intercept. Well, you know what? This is the x-axis, and it never crosses the x-axis, so there is no x-intercept. Determine the y-intercept. Okay, I cross the y-intercept on the y-axis. I don't know if you can see this or not. It's right here. Highlighted it so you can see it. That again is the point 0,2, so your y-intercept is the point 0,2. Determine the domain. Goodness, I made such a mess. Let me erase a little bit here. Okay, I guess that's good. Okay, the domain. From left to right. This is going downward, but it's also going leftward, which is negative infinity. The other side is going upward, but also to the right, which is positive infinity. And everything looks good. The line is solid everywhere. Right here it's filled, even though it's open above. You've got to fill the location when x is negative 1. So your domain is negative infinity to infinity. Your range, it's going downward forever and upward forever. So that looks about right, but we have a problem here. You have no y values. I need to highlight that. In this region, in all of this region right here, there's no graph low to high in this region. Left to right there is, but low to high you're missing values. Now you're solid on the lower side and you're solid on the upper side because of this point and this point. But between this, you're not good. So you're missing y values between negative 1 and 1. So in other words, your y values go from negative infinity to negative 1, and then they pick up at positive 1 back up to infinity. So this is your range. This is a little bit tricky, but that is your range because you're missing points, you're missing a graph in that yellow region from bottom to top. And I believe that's the end of it. So goodness, this was a long lesson. I hope you stuck with it all the way through. I hope you feel comfortable with functions, passing the vertical line test with, I'm trying to remember now what all we did, with X and Y-intercepts, with finding domain and range, with function notation, and all of these function values. So I think that's all we covered, and I hope that you feel good about this information.